This will go over a few of the other problems on the worksheet on section 2.2, which is mapping concavity and using the second derivative test. And we were applying this to a couple of these pictures. This is one we did in class where we found that there's a point sort of vaguely in there where the graph is changing concavity. We call that an inflection point. And concavity here means that the graph has a downward cup shape on that side and an upward cup shape on that side. And so the point in between is called an inflection point when we have that change. And it's a little hard to identify exactly where it happens, but with calculus, where we set the second derivative, find the second derivative and set it equal to 0, and find out that the second derivative changes from negative to positive at x equals 7,6, I believe was the number, we can actually find the coordinates of that point. On this graph, the one on the right, we do have an inflection point at 0. We definitely have a sort of a cup down shape that way and a cupped upward shape that way. But where the concavity changes after that is a little hard to tell. It's somewhere in that range where it starts to become cupped the other way again on the other side. So it looks like here there are 3 different inflection points, and so we can use calculus to find out what the x coordinates are for those. And this is one of the graphs that's on the second page. So we went through the first page in class. We're trying to map out where we have concavity changing, and so we do that by first finding a formula for our second derivative. So to do that, I first need to find my formula for our first derivative. So the first derivative here is 3x squared minus 6x, and so the second derivative is 6x minus 6. So the only time that's equal to 0 is when x is 1, and so I can draw a number line. This is going to be a sign chart, so it's going to be the sign of f double prime, and down here I have values of x. So I'll have x equals negative 1, x equals 0, x equals 1, x equals 2. So I have my number line and this value here, this value that makes the derivative 0. That's called a possible inflection point, because I don't know for sure that the concavity is changing there, but I'm going to mark that on the curve. So here's my possible inflection point. And so just like before, I'm going to test values, sample values to the left and the right of that value with the second derivative. So the second derivative at 0 is negative 6. The second derivative at 2 is positive 6. And so I can see that on the left side of the potential inflection point. What am I doing? I'll have negative second derivatives, and on the right side I have positive second derivatives. So the graph of f must have a concave down shape to the left of x equals 1 and have a concave up shape to the right of x equals 1. And so that means that there is an inflection point at x equals 1. So my conclusion would be that f is concave down on the interval minus infinity to 1. F is concave up on the interval 1 to infinity, and so therefore f has an inflection point at the point when x equals 1, and then the y-coordinate would be, remember to get the y-coordinate, I've got to come back to this formula. So 1 minus 3 is negative 2 plus 6 is 4. So at the point 1, 4, the graph has an inflection point. So this would be a good conclusion about concavity. I can tell you the shape of the graph on at any point, whether what's cup shape, and then tell you where the concavity changes. So you'd follow that process for each one of these problems, and I'm just going to erase what I have and do the second one. So if you need to stop and make a note, do it now or forever hold your peace. So in the second problem, again, we go through the same process. We need our first and second derivatives, so I'll just use the space I have. So the first derivative here is 8x cubed minus 24x, which means that the second derivative is 24x squared minus 24. And so our the places where we have the second derivative equal to 0. This happens when x is plus or minus 1. So we have two different potential inflection points, and so we want to check whether these are in fact real changes in concavity. So I draw my number line, mark a few points on it, -2, -1, 0, 1, 2, so that the potential inflection points are highlighted, and then that gives me my bins in which I can sample. So I'll have sample something from here, something from here, and something from here. Remember that the values down here are x values, and we are charting the sign of the second derivative, which is this formula up here. So when x is 0, that's the easiest one to check. When x is 0, I get -24. So f double prime of 0 is -24. And of course, I don't really care negative what, just that it's negative. So I'll be negative in here. F double prime of 2. This will be quite positive. So 24 times positive 4 is 96 minus 24, 72. So that's a positive number. And f double prime of -2 is exactly the same thing, if you plug it in. So positive numbers over here. So my function is concave up on the interval minus infinity to -1, concave down on the interval -1 to 1, and concave up again on the interval 1 to infinity. This means that that -1 and 1 are actually points of inflection, so -1 and 1 are inflection points. And to find out the y-coordinates, remember the y-coordinate here will come from the original f of x. So when x is -1, I'll have here 2 minus 12 plus 7, so that's -5. And when I put in 1, I get exactly the same thing. So this function is very symmetric, but looks like a big W, and so inflection points will be at these two values. Finally, the third of these certainly has the worst, is the worst for the derivative, so let's try to do it at least semi-carefully. The first derivative, this is one we've done before, but I'll just go ahead and write down the simplified answer. It should be 7 times 25 minus x squared over x squared plus 25 squared. This is one that we had done on the previous worksheet to see where the first derivative was equal to 0. And it is worth simplifying before you start taking the second derivative. The numerator here from the quotient rule comes out in pieces, and so you really want to write it as a simplified form before you set off taking the second derivative. The second derivative is going to use the quotient rule again. Let me just try to write out what you're going to get. We have the bottom, so the x squared plus 25 squared part, times the derivative of the top. Now the derivative of the top, this 7 is going to sit there, derivative of that is 0, derivative of that's -2x. So the derivative of the top is going to be -14x. Now I'm subtracting from that the top, so that's 7 times 25 plus x squared. And I'm going to multiply, that's 7, multiply by the derivative of the denominator. So that's the derivative of this, and that's going to involve the chain rule. So you might want to go over to the side to figure out what that is. But you're going to end up with a 2 times x squared plus 25 to the first power, and then I've run out of room, but there's also going to be a times 2x for the chain rule in there. So, and that's all over x squared plus 25 to the fourth. Remember, we're squaring the denominator. This is the denominator, and so it gets squared. Now you can see a few things factoring out of the numerator. There's an x squared plus 25 here. This is supposed to be a minus sign here. That's a minus. Sorry about that. But there's an x squared plus 25 here, there's an x squared plus 25 here, and so I can actually factor an x squared plus 25 out of this thing, which will cancel with one of these things down here. There's a minus 14x, and you can see I have minus 7 times 2x with a minus 14x sitting there, so I'd be able to factor that out. So if instead of exploding this thing out with FOIL, if you look for common factors first, you'll be able to simplify this most easily, and it'll end up being a minus 14x factors out of everything. I'll have 75 minus x squared left behind, and one of the x squared plus 25s will cancel out with one of the ones in the denominator. So I'll have x squared plus 25 cubed in the denominator. So that's how it should simplify my expression for f double prime of x. Now, this is easy to find where this is equal to 0, because once again, when we're trying to find out where a fraction equals 0, all that really matters is where is the numerator equal to 0. And so it's easy to see that that happens when x is 0, when x is the square root of 75, or when x is negative square root of 75. Square root of 75 is somewhere between 8 and 9. So on my number line, I'll throw down 0. That's a critical, it's a possible inflection point. Negative square root of 75 is out here. Negative 1 is in that bin. Negative 10 is out a little further. 1 is there. Square root of 75. That is supposed to be a 7. It's hard to. And then 10 is out here. So I have these places where my second derivative is 0 at negative square root of 75, 0, and positive square root of 75. So when I sample values in between, I'm just going to put them back into this because it's easiest. The denominator is positive all the time. So for example, when I put negative 1 in, f double prime of negative 1, it's easy to see that this is positive 14 and this is like 74. So it's a positive times a positive, that's positive. So I don't need to know what the actual answer is. I can just say positive. So those are positives out here. Oops, I'm sorry. That was negative 1 I put in. So positives out here above negative 1. So similarly, when I put 1 in for x, I'll have a negative times a positive, so that's negative, so I'll have negatives through here. When I put in 10 for x, this is going to be negative 140, and this is going to be negative 25, so that's a negative times a negative. So I'll have positives out here, and in some way I'll have negatives out here. So I can see that I have negative, positive, and so that gives me that the original function is concave up. So my original f is concave down from negative infinity up to the negative square root of 75, and between 0 and the square root of 75, my original f is concave up in the interval from negative square root of 75 to 0, and from the interval square root of 75 out to positive infinity. And so I do have inflection points at all three of these values. And if you go back and look at the graph on the front of this worksheet, this is the function that's graphed there, and you'll see that these are the positions of the inflection points that we were just sort of trying to guess at before. Now we have the exact positions of them.